After studying this module, you shall be able to know about the metal complexes of dinitrogen, the various bonding modes of dinitrogen as ligand, preparation of dinitrogen metal complexes, and also about the reactions of dinitrogen complexes. The metal dinitrogen complexes are coordination compounds that contain the dinitrogen as a ligand. Dinitrogen is very inert chemically, and few systems are able to reduce it catalytically under the mild conditions employed by dinitrogen fixing enzymes such as nitrogenase. Dinitrogen reacts with lithium and magnesium to give nitrides, but the only other non-biological reactions of dinitrogen under mild conditions is the formation of the dinitrogen metal complexes. More than 100 examples are now known, out of which many contains iron and molybdenum. The discovery of these coordination compounds containing the dinitrogen molecule as a ligand is one of the most exciting recent developments in the chemistry of nitrogenase. It is not that such compounds were unexpected. They have been so long in anticipation that most chemists have begun to believe that they could not exist. In 1930, Bottles showed that traces of molybdenum was essential for the growth of nitrogen fixing bacteria in the absence of any source of nitrogen other than dinitrogen. But in the presence of urea or ammonia, the bacteria appeared to grow happily in the absence of molybdenum. Thus, the molybdenum appeared to be directly involved in the nitrogen molecule in the process called dinitrogen fixation. This knowledge led to attempts to produce dinitrogen complexes by compressing the gas over molybdenum compounds, but with no success. Similarly, a development of interest in olefin and acetylene dinitrogen complexes during the 1950s led to attempts to prepare dinitrogen analogues of these complexes compounds of acetylene, but again they are of no avail. Indeed, all attempts to produce dinitrogen complexes were so negative that chemists were convinced that they would not exist as stable entities. But the energy levels of the molecular orbitals in dinitrogen provided sufficient reason in a form that the electron energy levels of dinitrogen differ from those found in any common analog molecule such as acetylene or dioxygen. This is important in two respects. First, the highest occupied molecular orbital is a sigma orbital and not a pi orbital. Secondly, the highest filled energy level is of a very low energy, minus 156 electron volt, whereas the highest vacant level is an antibonding pi level with a relatively high energy of minus 7 electron volt. The molecular orbital diagrams are shown here. The extremely low energy of the filled and the high energy of the unfilled orbital explains the unique character of dinitrogen. Neither reduction nor oxidation of dinitrogen is easy because it is difficult to remove electrons from the bonding orbital at minus 156 electron volt or to put them into lowest energy level, which is vacant, at minus 7 electron volt. The molecular orbital diagram of dinitrogen and dioxygen are shown here. Now we will see various bonding modes of dinitrogen. Dinitrogen as a ligand forms generally three types of bonding modes which are observed in dinitrogen complexes, such as The terminal one, where one of the nitrogen of the dinitrogen ligand is coordinated with a single metal ion. The other one is bridging mode. Bridging mode comes in two varieties. In one of the varieties, where both the nitrogen of the dinitrogen ligand are connected with a metal ion using a single bond, whereas in the other type of bridging bond, both nitrogen atoms are bonded with two metals via a double bond. Whereas in the third type of mode, the dinitrogen ligand can bind with a metal ion sideways using the pi electrons of the triple bond. These are the most common type of bonding modes of dinitrogen ligand. Now, in the terminal mode, in most of the cases, the dinitrogen shows a terminal bonding mode. The dinitrogen is terminally bonded by one atom, as shown in the figure. Dinitrogen in such cases is isoelectronic with carbon monoxide, as a comparison between the two ligands is also very useful. Carbon monoxide has a filled sigma lone pair orbital located on the carbon, with which it forms a sigma bond to the metal ions, and an empty pi star orbital for back bonding, whereas dinitrogen also has a filled sigma lone pair, but it lies at a very low energy than the corresponding orbital of carbon monoxide, probably because nitrogen is more electronegative than carbon. And so, nitrogen is a very weaker sigma donor as compared to the carbon of carbonyl ligand. Nitrogen also has an empty pi star orbital. Although it is lower in energy and so more accessible than the carbon monoxide pi star orbital, it is equally distributed over nitrogen 1 and nitrogen 2, and therefore the metal nitrogen pi overlap is smaller than the metal carbonyl overlap, where the pi star is predominantly located on the carbon. The result is that the dinitrogen binds very less efficiently than carbon monoxide to various metals. The group 6 transition metals such as tungsten, molybdenum, chromium are believed to have the greatest orbital overlap with end-on bound molecular nitrogen. The nitrogen molecule associates with it the metal center of either electron-rich low-valent metals or electron-deficient metals in higher oxidation states. Pi back bonding from electron-rich metal centers is the reason for the stability of molecular nitrogen association, whereas the sigma bond formation from the lone pair on dinitrogen is the stabilizing interaction for electron-deficient metal centers. The first dinitrogen complex to be recognized was the pentamino dinitrogen ruthenium complex, which was isolated in 1965 by Allen and Bottomley during the attempted synthesis of hexaminoruthenium from ruthenium trichloride and hydrogen hydrate, and it contained dinitrogen as a terminally bonded ligand, which was found later. The nitrogen-nitrogen distance of this and related nitrogen complexes is only slightly different. It comes in the region of 1.05 to 1.16 angstrom from that of nitrogen-nitrogen distances in the free dinitrogen molecule, which is actually 1.1 angstrom. An important property of the mononuclear complexes is the strong IR absorption due to the nitrogen-nitrogen bond stretch at in the region of 19202 to 2150 centimeter inverse. Free dinitrogen is inactive in the air in IR, but binding to the metal causes a strong polarization of the molecule, with one of the nitrogen becoming positively charged, whereas the other nitrogen is negatively charged. This contributes both to making a NN stretch IR active and to the chemical activation of the nitrogen molecule. Now we'll see bridging mode. Because the two ends of dinitrogen are similar, the molecule can easily act as a bridging ligand between two metals as shown in the figure. If the back donation is large, the dinitrogen ligand can be reduced to a hydrazide complex. Some examples of complexes in which dinitrogen bridges to two metals are shown here. We can see that in the ruthenium case, the system resembles to that shown previously in the other complex, where the nitrogen-atom distance is little different in length from the terminal nitrogen-atom distance as shown in the nitrogen pentaamino ruthenium complex itself. Some dinitrogen complexes are appreciably basic at the second dinitrogen, showing once again the strong polarization of the second nitrogen. These can bind Lewis acids at the second nitrogen to give adducts, some of which have very low nitrogen-nitrogen stretching frequencies, and these seem to resemble. A number of examples are shown here, and we can also see the higher stretching frequency of the dinitrogen ligand in such complexes. In the first complex, the rhenium complex, it is actually 1925 centimeter inverse, whereas in the rhenium molybdenum complex, it is 1680 centimeter inverse. Now we'll see what is the side-on mode. The side-on bonding mode is rare. First side-on dinitrogen complex was synthesized by Ozin and van der Voort in 1973. As the first side-on dinitrogen complex crystal structure was determined by Crisse in 1982. The structure of this complex is shown here. In this complex, dinitrogen binds in neta1 and mu2 neta2 fashion to form two dititanium units. Side-on overlap gives other ligands access to both nitrogens, 5-star molecular orbitals. Some other examples of the side-on complexes of dinitrogen are shown here. For side-on mode of bonding of dinitrogen, more electrophilic early transition metals are often needed, and as lower row transition metals are larger in size, so they provide enough space for side-on dinitrogen binding. Ligands around the metal center should be finely tuned as spacings and electronics around dinitrogen binding site strongly affect the bonding mode and the degree of activation of dinitrogen. Metallocenes, for example, happen to have correct steric and electronic factors to facilitate end-on binding of dinitrogen as ligand. Now we have seen the types of binding modes of dinitrogen in its metal complexes. Now we'll see the methods of preparation of these complexes. Common preparative routes of dinitrogen complexes are reduction of a phosphine substituted metal halide in the presence of dinitrogen. You can see few examples. Degradation of a nitrogen containing ligand, and also by displacement of labile ligand by dinitrogen. Dinitrogen can often displace neta2 dihydrogen. If this were the last step in the catalytic cycle, it would explain why nitrogenase always produces at least 1 mole of dihydrogen per mole of dinitrogen produced. We can see a lot of examples here where magnesium DP is used as reducing agent. Now we can see reactions of dinitrogen complexes. Quickly we'll see what type of reactions does dinitrogen complexes show. For example, hydrogenation. One of the most basic dinitrogen complexes, notably the bis dinitrogen molybdenum and tungsten complexes, can be protonated. According to the exact conditions, various hydrazine complexes are obtained, and even in some cases, free ammonia and hydrazine is also produced. As strongly reducing molybdenum 0 and tungsten 0 complexes, the metal can apparently supply 6 electrons, and so the metals are oxidized during the process. We can see in this equation the loss of the very strong NN triple bond is compensated by the formation of two NH bonds and a metal nitrogen multiple bond. The mechanism was explained by chart and has been proposed for the dinitrogen reduction observed in these experiments. Dinitrogen is a net electron acceptor from the metal, and so loss of first dinitrogen leads to the metal acquiring a greater negative charge and thus backbonding more efficiently to the remaining dinitrogen, which is therefore polarized and activated even further. To be noted is the fact that the final NN bond breaking is again accompanied by the formation of a metal nitride. Such species are known to hydrolyze easily to give ammonia. It is likely that natural systems may also undergo by similar intermediates. The steps of the reactions are shown here. Greatest weakening of the NN bond is also expected for early D2 metals, which backbond the most strongly to pi acceptor ligands. For example, the titanosin reacts with dinitrogen to form a dinitrogen complex, seems to have a neta1 and neta2 forms and protonates with HCl to give hydrazine. These examples shows different dinitrogen frequencies in the IR at 2056 and 2023 centimeter inverse respectively. And most significantly, the N15 NMR shows two mutually coupled resonances for the neta1 and a single resonance for the neta2 form. The coupling constant for the neta1 form was 7 Hz. Schrock et al. Have made various metallocene complexes using dinitrogen where the back donation is so strong that the dinitrogen is now effectively reduced to a hydrazide tetraanion, as shown by the NN distance of 1.235 angstrom in the molybdenum complex. Ammonia is formed with lutridine hydrochloride as proton source and zinc amalgam as reductant. Dinitrogen can also be reduced to ammonia at room temperature and 1 atmosphere with the molybdenum catalyst, where the ligand is a trianionic tripodal triamide. Addition of a lutidine salt as proton source and a decamethyl chromosine as reductant gave 4 catalytic turnovers. In this system, dinitrogen is reduced at a sterically protected single molybdenum center that cycles from molybdenum 3 to molybdenum 6. The zirconium, hafnium, octamethyl metallocenes containing side-on mode of dinitrogen bonding undergo reduction of dinitrogen under fissile conditions, which is shown here. Zirconocene performs first hydrogenation at ambient conditions while needs higher temperatures to hydrogenate fully. On the other hand, hafnocene performs first step faster and needs higher pressure, but both the processes require presence of alkali amalgams. We can also see the functionalization of dinitrogen complexes beyond hydrogenation. For example, the carboxylation and alkylation. The dinitrogen complexes, for example, the zirconocene complexes of dinitrogen can also react with carbon monoxide to show carbonylation, and they can also react with various alkenes to show alkylation reactions. Nitrogen fixation in biological systems. The enzyme system responsible for fixing nitrogen is nitrogenase. Nitrogenase plays the vital role of fixing gaseous nitrogen and making nitrogen compounds available for plants. It is distributed in a group of symbiotic bacteria and also in non-symbiotic or asymbiotic bacteria. Symbiotic bacteria are those which are fixing dinitrogen is in association with plants, such as the bacterium rhizobium, which is associated with the nodules on the roots of leguminous plants. Asymbiotic bacteria are certain free-living bacteria which can fix atmospheric nitrogen, such as azotobacter. The enzyme isolation from the sources mentioned above are among the first, most complicated of all enzymes. Long and intensive studies have been revealed that nitrogenases are composed of two proteins. One is called a molybdenum iron protein and the other is only iron protein. The enzymes isolated from the source mentioned above are among the most complicated of all enzymes. Long and intensive studies have revealed that nitrogenases are composed of two proteins. One is the molybdenum iron protein, whereas the other is only iron protein. They are not active individually. The molybdenum iron protein contains molybdenum as well as iron sulfur groups, and the iron protein is an iron sulfur protein. The smaller iron protein has a molecular weight of 57,000 to 73,000 and contains Fe4S4 cluster. The larger molybdenum iron protein has a molecular weight of 2,20,000 to 2,40,000 daltons and contains both metals, 1 atom molybdenum and 32 atoms of iron. Iron molybdenum protein further consists of molybdenum iron cofactor and protein P clusters, which are shown in the figure. Iron molybdenum cofactor structure model is recently deduced from single crystal X-ray analysis for iron molybdenum proteins of Azotobacter, Vanillandi and Clostridium posturinium, which contains the cuboidal Fe4sp3 and Fe4MOS3 unit bridged by 3 sulfides. Dinitrogen molecule binding to the active site is still uncertain. At a glance, a triangular prismatic cavity surrounded by 6 coordinatively unsaturated iron atoms seems to be susceptible to dinitrogen insertion, giving the mu6 dinitrogen ligand, but the cavity size is considered to be too small to accommodate dinitrogen. Alternatively, extended Huckel type calculations suggested that coordination of dinitrogen rather to the edge or the face of the Fe6 triangular prism as a bridge between two cuboidal units. On the other hand, coordination of cyanide to the isolated FeMO cofactor has been reported to take place at the molybdenum atom from the X-first criteria. Electrons flow from a reducing agent to the iron protein into the molybdenum iron protein and finally onto the substrate. Magnesium ATP, which binds to the iron protein, is hydrolyzed as a substrate, is reduced. The precise time at which magnesium ATP binds and dissociates and the exact role it plays in the reduction process have not been fully elucidated. The electrons that are utilized to reduce the substrates come through the enzyme. Ultimately, from such electrons, donors are ferredoxins. In vitro, nitrogenase requires the delivery of considerable amount of energy by the act of ATP hydrolysis. The ATP requirement is highly specific and no other nucleotide works. For every dinitrogen reduced by nitrogenase, one hydrogen is produced and as an unexplained waste of electron by the system. Indeed, some organisms incorporate a hydrogenase to recycle some of this hydrogen. The stoichiometry of the biological reaction is shown here. Now we can summarize. The dinitrogen complexes are known for early or middle transition elements with dinitrogen displaying either terminal, bridging or side-on coordination modes. Some of the complexes activate the rather inert dinitrogen for further functionalization. However, the hydrogenation reaction is facile only in a few instances and cannot compare to biological nitrogen fixation. Still, the dinitrogen complexes of transition metal serve as suitable models for active sites of nitrogenase and provide a suitable platform for further improvisations to enable conversion of dinitrogen into hydrides, as well as functionalization for conversion into other useful molecules.